Hi viewers, welcome to our electrical engineering lectures channel for most interactive sessions of different subjects of electronic and electrical engineering. For the latest updates and videos, don't forget to subscribe and click the like button.
If nyquist criteria is not met, there will be distortion, and technically this distortion is termed as aliasing. So aliasing will happen when omega s will be less than 2 omega naught. As an example, just consider over here, we select a sampling frequency which doesn't meet the nyquist criteria. Then in that case, xs of j omega will be what? For example, here is omega naught, the right sided impulse, and the left sided here is minus omega naught. And for example, let's say omega s is somewhere over here, omega s. So in that particular case, the left sided copy will come over here and the right sided copy will go over here. Similarly, on the other side, here is minus omega s, so the right sided copy will come over here and the left sided copy will go over here. Now this is basically the point which is equal to omega s by 2. So now if you place a filter having bandwidth of omega s by 2 over here, then definitely you will not be recovering the original you will not be recovering the original signal. Rather, you will be recovering a signal having different frequency, and this frequency is equal to omega s minus omega naught. So instead of recovering the signal with the desired frequency omega naught, you will be recovering a signal with changed frequency, which is omega s minus omega naught, which is basically the result of aliasing. So after the filtering, this signal comes out to be cos omega s minus omega naught into t, which is not definitely the original signal, which is aliased signal. Right? So that is the concept of aliasing. And now we have already discussed the mapping from n to t, and that expression was t is equal to n capital T, or n is equal to t over capital T. But now we also discuss the mapping between a continuous frequency and discrete time frequency. To understand this concept, let us write the expression for xs of t again here. Xs of t is equal to summation n minus infinity to infinity xc of nt multiplied with delta of t minus nt, and the frequency domain expression of xs of j omega, that is given by the CTFT, and that CTFT is given as n minus infinity to infinity xc of nt multiplied by e raised to power minus j omega into t into n. So this is basically formulation of CTFT. This is formulation of CTFT. And if we take DTFT of the sampled signal, the sampled signal was x of n, because it is discrete time, so we cannot take CTFT. We have to take DTFT, and that DTFT will be equal to x e raised to power j omega equals summation minus infinity to infinity x of n e raised to power minus j omega n. This is the formula of DTFT. Now if you compare these two formulas of DTFT and CTFT, what is the similarity? The similarity is that the left hand side will be only equal to each other if we set these two parameters equal to each other, because all other things are the same. All other things are the same. These are also same, because after the sampling they have defined only at the integer values of time. Just we have divided with the sampling period capital T. So in order to make these two things equal, I can write here that x of e raised to power j omega is equal to xs of j omega when small omega is equal to capital omega into t. So that is basically the relationship between the analog and digital frequencies. That is very important to comprehend. This omega here is discrete time frequency having unit of radians. This capital omega is continuous time frequency having unit of radians per second, and this capital T is the sampling period having unit of seconds. So this is the conversion. If we follow this conversion, we can finally write that xs of j omega, it is equal to 1 over capital T, the expression we have already written, k xc of j into omega minus k omega s. Now, using the fact that capital omega is now equal to small omega over capital T, we can also now draw the DTFT, because all this exercise we are doing is to plot the DTFT of the resulting sampled signal. So that will be equal to 1 over T summation k, and here it is xc of j. In place of omega we will have small omega over capital T minus k 2 pi k, because omega s was equal to 2 pi, so it is 2 pi k over capital T. So that is the main governing equation of the DTFT of the sampled signal x of n. It means that the spectrum we have already drawn in here, that is still a CTFT. In order to have the DTFT of the sample signal, we need to have one more conversion, and that conversion will be highlighted this particular example. Now we take the same cosine which was already defined. Here we take specific value of omega naught. Let us take it as 4000 pi into t. So it is the same thing with omega naught equals 4000 pi radians per second. Now we have to take omega s. In order to avoid aliasing, we have to take omega s greater than or equal to 2 omega naught. 2 omega naught here is equal to 8000 pi. To be on the safe side, we select omega s as 12,000 pi radians per second. If we select this one, then capital T comes out to be what? Because capital T will be equal to 2 pi over omega s. So it will be equal to 2 pi over 12,000 pi, and we come up with 1 over 6,000 seconds, which is the sampling period. So this is how you select the sampling period. Now, first of all, we draw xs of j omega by using the same concept. First of all, the original copy. The original copy will be coming at 4000 pi and minus 4000 pi, and the sampling frequency is equal to 12,000 pi, which will lie over here, and one copy here and here. So this point will go at 8000 pi, and this will go at 16,000 pi. This is capital omega. And similarly on the other side, if it is minus 12,000 pi, so it will go to minus 8,000 pi, and it will go to 16,000 pi, and with the amplitude having pi over capital T. So this is the step where we haven't divided by capital T. Now, in order to convert this CTFT into DTFT, we will use this mapping. Small omega is equal to capital omega into T. So in order to convert the above axis, which is of capital omega, we will multiply the axis, multiply the omega axis by capital T, which is equal to 1 over 6,000 already found. So after doing this, what will happen? We just multiply by 1 over 1000 to come up with this thing. All the things will remain the same like this, but this point will go to 2 pi by 3, and it is minus 2 pi by 3. and this point omega s, this point will become 2 pi after multiplication with 1 over 6000, and this point will become 4 pi by 3, and this point will become 6 pi by 3. Similarly on the other side, here it is minus 2 pi, and it will become minus 4 pi by 3, and this will become minus 6 pi by 3. Now if you place a filter over here, and what is the point where the filter is placed? It is placed as omega s by 2, and in our case omega s by 2 was equal to 6000 pi. So when it is converted, it will become pi, and this point will become minus pi. So the filter will be placed over here. Filter will be placed over here. This was pi over capital T. Filter gain is equal to capital T. So now this particular plot is of the DTFT x of e raised to power j omega. When we recover this signal, only these two impulses will pass through this filter, and the signal, discrete time signal, will be cos 2 pi by 3 n as per the formulation. So this is basically your sampled signal. X of n is equal to this. But if the sampling frequency was not the desired one, if the sampling frequency was not the desired one, for example, we select let's say omega s equal to 3000 pi. If we select omega s equal to 3000 pi, then t comes out to be 1 over 1500 second. Now if we multiply this particular plot, the x-axis of this particular plot, with 1 over 1500, then what will happen? Just we are going to see the effect of aliasing. If you multiply it by 1 over 1500, then what will happen? This point, which was 4000 pi, it will be converted into 4000 pi multiplied by 1 over 1500. It is cancelled out. It is 8. First of all, we just make the original copy. Sorry, the original copy comes over here, and the sampling frequency, which was 3000 pi. So 3000 pi is, let's say, over here. If 3000 pi comes at this point, then what will happen? That we will have बात सुन, ये तू ठीक कर लेगा ना? बीच में प्रॉब्लम हो गई है. 4000 pi. $6,000 pi. Subscriber seven. कितने मिनट की बनाएगा? pi भी कहाँ चला गया? नींद आ रही है. एक मिनट ठहर जा. अगर इसको मल्टीप्लाई करें कितना तो 4000 पाई था, 6000 रख लेते हैं. 6000 रखा, 6000 3000 4000 रख लेते हैं. एग्जाम्पल डिफरेंट कीजिए. Okay, so now we take another example, and let's say we have xc of t is equal to cos 1000 pi t. So here omega naught is equal to 1000 pi. And now, as per Nyquist criteria, we need to have sampling frequency greater than or equal to 2000 pi. Okay, now to see the effect of aliasing now in the same example, let us select now omega s. Instead of meeting the Nyquist criteria, now we select omega s equal to 3000 pi, which results in the sampling period t of 1 over 1500 seconds. Now what will happen? Let us draw again the spectrum of xs j omega, and at this point, first of all, again now we will have the copies, and the original copy is, let's say, here at 4000 pi and minus 4000 pi. Now what is the value of omega s? It is 3000 pi. So it means this is the point which is omega s equal to 3000 pi. Now the copies will be shifted at integral multiples of this 3000 pi. So now the right sided copy of this around this 3000 pi will go to 7000 pi over here, and the left sided copy will go to minus 1000 pi here, minus 1000 pi. Similarly, for minus omega s means minus 3000 pi, the right sided copy will go to 1000 pi, and the left sided copy will go to, and let me use a red color for this, it will go to minus 7000 pi. Let me replace this one copy with also red, because these are the left copies. Now what is the value of omega s? It was 3000 pi, and half of this value is 1500, and 1500 may be like this. If it is over here 1500 pi, this is required to select the filter. So the filter will be placed here. So now you see, if we apply the filter at omega s by 2, now the recovered signal is 1000, having frequency of 1000 pi. It means that the signal is changed. So it is corresponding to cos 1000 pi t. So that is the consequence of the aliasing. Now what will happen if we convert it into DTFT? For the conversion from CTFT to DTFT, again we will use small omega is equal to capital omega into t, and here t is equal to 1 over 1500. So we multiply the x's, this one, with capital T. So when we multiply it with capital T, this point, which was 1000 pi, corresponding to this, that will be now 2 pi by 3. This point, which was 4000 pi, over here, and this point is 2 pi, and this point is minus 2 pi by 3. So if you just draw the impulses over here, here impulse will look like this, and here it is this one, and the filter was placed here. So now the frequency of the filtered signal is 2 pi by 3. So the so the sample x of n comes out to be cos 2 pi by 3 n. It means even we have aliasing. In that case, there will be two true drawbacks. The first drawback is the frequency of the signal is changed, and the second problem with which aliasing does is that due to aliasing, different sampling frequencies can result in a same frequency discrete time signal. Because you should note that in the previous case, when we selected the sampling frequency of 12,000 pi, the resulted discrete time signal was cos 2 pi by 3 n, this one. And when we selected omega s equal to 3000 pi, even in that case, we resulted with the same signal, cos 2 pi by 3n. So this is the second problem. So you can summarize these 2 points like this, that aliasing causes frequency change in the sampled signal, number one, and number two, it also generates the same frequencies in discrete time signal for two different frequency continuous time signals. So that are the two problems that aliasing causes. And the last point regarding this sampling process, which is very important, is that we have already discussed that as a consequence of sampling, the original CTFT of the continuous time signal is shifted at integral multiples of omega s. But what happens in DTFT? To see this, just look at this particular DTFT over here. If you see what is the mechanism of the generation of copies here, in DTFT, the copies will be generated at integral multiples of 2 pi. So this is the original copy, this is the copy around 2 pi, this is the copy around minus 2 pi, and so on. And this is the reason why we say that DTFT is periodic with period 2 pi. So the same point, which is by definition true for DTFT, is also verified from this point, that when we convert from CTF to CTFT to DTFT, the resulting signal will be periodic with period 2 pi, because all the copies because the original copy is now shifted at integral multiples of 2 pi. So that was all about the sampling process. In the next lecture, I will be showing you the process of reconstruction, followed by decimation and interpolation. Thank you so much.